Hey, how's it going? Thank you for tuning in. I'm just getting set up here. We're going to basically go through and do a study session for a lab related to linear regression cost function. This is just like an informal study session, so please don't come here for a tutorial, but I will definitely be trying to share little things here and there that might be helpful if you're on your journey. If you would like to study with me and follow the course that this is based on, all you have to do is go to this page. It's down in the description. This is a course I'm taking that is sponsored by Deep Learning AI and Stanford University on supervised machine learning, regression, and classification. And you'll be able to follow along with the course. They have built-in labs, but for this study session, I'm actually doing my own version of their labs in my Jupyter notebook. As a precursor to this, if you are going to try to do this or follow along in your own Jupyter notebook, two things you need to make sure are set up in order for these dependencies to work. The first one is you see here where this matplotlib is. There's some dependencies that you need to get, and it'll throw an error if you don't have them. So that's one thing. And then for this, you see it says from lab utils uni. You actually need to have some Python code that is in your environment for this, and I put a link to where you can get this off of GitHub. This person has very kindly posted this with all the functions and everything available. So it won't work unless you have that for what we're doing today. What we're doing today is we're going to be taking the cost function formula that is described here. This is the squared error cost function, and we're going to be converting this into Python code so that we can run it against a set of data and then analyze whether or not our regression line for linear regression best fits our data. So if you are not familiar with this topic, or you're just like learning and you would like to get some more information about what linear regression is or what a cost function is, all you have to do is go back and look at the first two videos in this playlist, and I describe that in those videos. So I won't spend too much time talking about that today, unfortunately. I'm just going to switch my theme here over to dark mode, and then we can get started. Okay, so this is the formula that we're using, and then what we're creating today is we're making a plot for a cost function that's going to involve both this like regular plot and also a three-dimensional interactive graph, and we're using Jupyter Studio to do that. I'm sorry, Jupyter Notebook, not Studio. So I'm gonna close these. Yeah, just check the stream notes if you want any more information though. Okay. Okay, so we have a problem statement that we're going to work through, and I'm just going to type that out here. Actually, I'm going to just copy this because I don't need to type this part out myself. Okay, so you would like a model which can predict housing prices given the size of the house. Let us use the same two data points that we did in the previous lab. A house with 1,000 square feet sold for $300,000, and a house with 2,000 square feet sold for $500,000. And we're reducing these numbers by dividing them by 1,000, so we get 1, 300, 2, and 500. So the first thing we need to do is like store this data, our x and our y, inside of some variables so that we can use them later on in our code. So that'll be the first thing I do here. So I'm going to call the first variable xtrain. Train stands for training, since this is going to be the input for our model. And up here I sort of describe here x is the input, whereas y, there are two y's. There's the y hat and the regular y. y hat, which is the y training data, that is the output of the model. And then the regular y without the hat on it is like the output of the prediction. Okay, so np.array. When you're using the NumPy library to create arrays, we're treating these as floating points because they are, because they are reduced from the thousands. We're treating it as floating points, so you can do like 1.2, and that would be like 1200. I don't know if that's like a limitation on the NumPy.array, but since NumPy.array or NumPy in general is kind of created to be like for scientific calculations, a lot of scientific calculations are, floating points because of the accuracy. So it seems a little useless in this scenario, but it's likely to not be useless in other scenarios. And actually, I don't know if it will like break if we don't do floating points. I'm just gonna see. No, it seems to work. I think you would have problems with like type coercion though, potentially. I don't really know how Python works in depth, to be completely honest, but it'd be interesting to kind of see if there would be like problems with type coercion if you want to take an integer and break it up into like, smaller pieces that are not integers. So I'm just going to comment here. This is the size in 1,000 square feet. Oops. This is the price in $1,000s of dollars. Okay, so the next part of this is we're going to compute the cost. Oh, I got to change this to Markdown. My bad. Okay, so the term cost in this assignment might be a little confusing since the data is housing costs. Here, cost is a measure of how well our model is predicting the target price of the house. The term price is used for housing data. So what this is saying here in this section here is like the topic of this study session, this lab, is cost function. And in terms of this like linear regression, the cost function, I can show you my notes here. I think it's in this. No, actually, I was in the right document. The cost function is basically a summation of the differences between the regression line and all of the scatter points in the training set. So for every XY coordinate that falls along the regression line, that is coordinated with the XY coordinate of a plot point here. And so like if you see here, right, like this, for example, this scatter point here, this shares a position along the x-axis with some point along this regression line, right here. But where it shares a point along the x-axis, there is a difference in the y, the value of the y axis, right? So for this one, this would be like maybe like 180, 175, and then the same position along the regression line is probably like 150. So the difference between those two numbers would be like, I don't know, like 30 or 25 or 30, right? So that number, that 25 or 30, which is the difference between the y of the plot point and the y of the regression line, that is called the cost. Well, the cost is like that number for all of these points added up together. That's the cost, and then for any single point, that's the error of that point. So this is just saying, like, don't get confused, because when we talk about like money and purchasing things or like houses and stuff, usually we talk about costs in the context of that. But here we're gonna differentiate by calling the price, the cost of a house, like the actual money you pay for a house, we're gonna call it the price, and we're gonna call the cost the actual error of our regression line to our data set. Okay, so the equation for cost with one variable is, this is the formula here. I explained this formula in the last, in part 1 of this series here. And then it says here where we take an index from the X column, which is this here, the square footage, where we take an index from that and we assign it some coefficient of weight and bias, and we don't know what that is yet. We don't know what the weight and the bias are yet. So the formula for, or the function of x with regards to weight and bias is our prediction. That's our model for every iteration through the data set for all the x inputs. And this is the squared difference. So we take the difference here. This right here, by the way, this function, this could also be represented by y hat. This is just like the long, or maybe like the medium version of y hat, but we're taking the difference between like y hat minus the actual prediction, and then we're squaring that. That's what it's saying here. These differences are summed up all over all the M examples. M here is the size of the array that contains our entire training set, or all the rows for a training set. And remember, those rows correlate to one X and one Y, one X input and one Y output. And so there's a size to that. For this example, our size is just 2. Even though there's 2 different arrays here, there's the size of M, which is our training set, is 2, because there's an input and there's an output. There's a thing that's going in, and there's a set of things that we know for sure we should get out. And then we're basically taking these correlations and we're abstracting them to make an assumption for some future unknown input. These differences are summed up over all the M examples and divided by 2M to produce the cost. Note, in lecture summation ranges are typically from 1 to M, and code will be from 0 to M minus 1. What this is saying here is that, so like in mathematics, in mathematics, mathematics indexes things with a zeroth index, whereas in code, mathematics indexes things from like 1 up. So like the first item in a set in mathematics is the first index, whereas in code, a code is typically 0 indexed. So like with Python, the first item in an array is the 0 index. So that's what this is saying here. It's just kind of a reminder. So even though you see here in the formula, it says that the minimum is the starting index. It says here 0. This is actually going to be 1 when we turn this into code. And the maximum here is M minus 1 to accommodate for the fact that our index is 0 indexed. Hopefully that makes sense. And actually, I need to update that in my notes here because I have that wrong. I know I have that wrong. Yeah, it should be... myself. Okay, I think it was right here. So 2M, sum, limits. I'm gonna put this in brackets. So M minus 1. I think I might have that here too. Let me just go ahead and fix this real quick. This is latex, which is like a syntax for describing math notation, by the way. It looks pretty intimidating, and it kind of is if you don't have like auto completion, which I don't in this particular app. But once you get used to it, it's not so bad. It's like, I find it kind of fun. It makes me feel like a nerd, which I like that feeling. So I'm just updating all of my notes here where I have this, just so that when I upload these into my blog later on, it's not like misleading or inaccurate. Here's another one. I'm going to put all these notes on my blog. In the meantime, I tend to put them on LinkedIn. If you go check the description for this stream, you'll be able to see the links to my LinkedIn and also to my link tree where I post that same link as well as my blog link. So check there. I don't know when I'll post these, but it'll probably be sometime this week. By the time you see this stream, it'll very likely be posted on my blog. Okay, so I think I got all the places here where I had an issue with my formula. So yeah, back to this. So m-1 and is the maximum, and I equals 0, that's the minimum. These basically describe how this summation is going to iterate over the entire set of data. The way that this translates to code is that this represents a loop where ooh, I can't highlight this. So you see where it says like FWB. So this part right here, this is going to perform a loop over every X, Y pair in our training set. And it's going to add up whatever these values evaluate out to. It's going to square them, and it's going to add all of them up for every single row within our training set. So for every row, this is one row and this is one row. It's going to do that. And then it's going to take the value that is created from doing that, and it's going to divide it by 2m, where m is the length or the size of our training set. We're going to be instead of like making one two-dimensional array that includes both our x's and our y's, we're just going to use our x training data to get this m, because we know that our y training data is always going to be the same size as our x training data. So m is basically going to be the size or the length of x trained, of this x trained here. Okay, so next part. I'm just going to put some notes here for your edification. You're going to see here F_WB. This is, you know how I was saying before that there's this distinction between Y and Y hat. Y is an actual prediction, whereas Y hat is the prediction, or is the, it's like the modeled, it's like the modeled output that correlates to an X input in our training set. So this function of weight and bias, this is like saying f of X. This is like saying this right here, basically. So when you see this F, when you see this F_WB, this is an actual prediction. And this is the different, let me just make a list here. So this is the difference between the target and the prediction that is calculated squared. So basically, this f underscore WB, this in the context of doing cost function, not necessarily doing a linear regression line. So in linear regression line, we might use this f underscore WB, but when we use it in that context, it means this here. Sorry for if that's confusing. But since we're doing cost function and not linear regression, this function of WB actually is going to mean this instead. So it's like a placeholder basically. And when it says like the difference between the target and the prediction, the target is this y hat of whatever index minus y of the index. So that's the target, and then that's the prediction. Sorry, I think I might have said that backwards a few moments ago. Please forgive me. Okay, so that's why this is a study session. Okay, so and then this is going to add each of the iterations of M to create a total cost, and then which is going to be divided by one over 2m. Okay. And I'm just gonna break this up a little bit so it doesn't look like it's a part of the notes above. Okay. So that's our explanation of what we're doing with this cost computing. Okay, now let's just do some code. We're gonna compute the costs. We're gonna write out the loop and the function for the function within a loop. I'm sorry, the loop within the function for computing the cost. I'm probably gonna come back and do a review video for this, by the way, since I am doing this for the first time live. I don't want people to walk away with this being the definitive explanation. So I'll come back and do a review video of this later on, which I think will help for anyone who's actually coming here to get information instead of just to study with me. Think of this as like me just like being your study partner. That's really what I feel like this is. When I make these videos, it's because it helps me to like talk out loud and explain things. And since I already went through the course and watched all the modules, like this is kind of my way of reviewing. I actually come back and watch these videos a lot. So, okay, so this computes the cost function for linear regression. Just writing some notes here. We have 4 different arguments, and I'm going to basically write out like what these arguments represent, just for learning purposes. Okay, so the first one is the x. This is a array here. So this right here, this array. And this m here is the size of the array. Basically what this is saying is that this is a data structure. This is some data that is being input into our system. And within this array of data, there are m number of examples. We don't always know the size or the number of examples, and that number can also change as the algorithm grows. This number could change. Machine learning algorithms tend to have data sets that can fluctuate over time. So the next argument is, similarly, it's the y. I'm terrible at typing. Okay, so these are the target values. The target values, it just means like whenever you're doing the training part of your algorithm, you're providing it an X input. And for the training part, you're telling it that each of these X inputs has a specific Y outcome that we know for sure correlates with it. So those are called the target values. And then W and B, these are scalars. A scalar is just an array that consists of two values. In physics, it's like a magnitude and a direction, but really it's just a two-dimensional array. It's a scalar. And I want to get my colons in the same place. So this is model parameters. In the math notation for this formula, in the math version of this notation, it will look like this here. I don't know if that's easy to see. It'll look like this here. So the W and the B, the weight and the bias is here. And this could be passed in as like an array, but in the case of this particular function, these are just being passed in separately. But they could be passed in or coupled together. That wouldn't really make a huge difference either way. Usually when you say scalar, you're talking about them being coupled together. But that doesn't appear to be the case with the way that this little lab is like written out. So I'm not sure why they call it a scalar. That is a little bit confusing from like the math standpoint. Okay, so this function is going to return something. It's going to return the total cost. And that total cost is going to be a value, like a number, that we are trying to get the smallest number for. That number, it should be as small as possible, and the smaller that number is, then the higher the integrity of our linear regression, which means that it's going to more accurately predict something given some novel or unknown X that we're passing into it. So the cost of using as the parameters for linear regression, we'll break this up. Okay. M equals x dot shape. Dot shape is a method that comes from NumPy, and basically what it's going to give us is a length, the size of the array for our X training data, which is this here. And this 0 here is just saying that it's on the 0th dimension, because remember, this NumPy dot array, it could be multi-dimensional, meaning that you see how it says like 1.0? It could be like 1.0 and like 3.5, 3.6 or something, or like whatever. But since we're doing univariate linear regression, we're doing this analysis over a univariate linear regression, we want to make sure that we only address the first, or the 0th index, which is the first one in that one-dimensional array. It seems like redundant, and really, if you wanted to, you could just call it the length method in Python, because it seems a little bit like unnecessary, but that's just how this method works. So M is just going to be the size, which is the same thing as the maximum minus 1 in our summation notation there. So the cost is going to be set to 0. What we're doing here, this is not the actual cost that we're outputting. This is going to be a placeholder. So this is going to be, what we're doing right now is called mutable programming. It's like a mutable, how would you describe that? It's a mutable paradigm. I don't know if that's the right word. That just means that we create a data structure, or we create some variable, and then we just change it instead of creating a new one every time. I'm not sure exactly like the reason why we're doing it that way. I know like in some programming languages, you have to reserve memory, you know, to create more efficient runtime. I don't know if that's true for Python. I'll have to look into it. So we're gonna like do our loop now for the index, for each index in the range of m. So it's saying that for this array, for each index in the range of m. So that's saying like if this number here is like 2, which it'll be in this case, then we're gonna do this each time, and that will be like for each of these indexes. And each of those indexes is going to have a number that will allow us to iterate. This right here is, oops, I did the comments from like Java or JavaScript. Okay, so this right here is the linear regression formula for a row. Remember, we're going to do this for every row within our data. A row is like an index, basically. By the way, I call it a row because if we were to look at this as a data table, our x values would be in this column, and then an x and a y together would represent a row. So index and a row is kind of interchangeable in a sense. Okay, so that's what this right here represents. This is the formula for linear regression in regards to the x input at a specific index within our training data. Okay, so the cost here, the cost formula is what we're talking about here. So I need to look something up really quick. I don't know what a double star means in Python. I think it means to divide. That would make sense. Let me just put some parentheses around this. I'm gonna open up a new thing here. I'm just gonna tinker with this real quick. I really have an aversion to reading documentation, so I want to just do it myself. Okay, so oh, that means squared. Duh. Okay, my bad. That was me having some mental failure for a second. It means squared. It just means like take it squared. 2 by 2. Okay, so what this is saying here is like we're gonna take this is the output of running the linear regression for a specific index on X, and we're going to subtract it from whatever the Y value is within our training. this mixed up. I'm getting this mixed up. 1 second. Okay, yeah. Okay, so I think I had this. I think I had this backwards once again. Yeah, I definitely have to do like a little review video of this after. I'm going to change the name of this to like to make this very clear. This is a study session and not a tutorial. Okay, so earlier I think I was saying this a little backwards, but this y hat, this is actually a prediction. This is like when we create our model and we run it against some unknown x and we make a prediction. If it's just a regular y, then that is like a correlate to some like data that is from our training set. So what we're doing here is with the cost function is we're taking the prediction that we get from some x, and we're going to subtract it from some actual training y, you know, and then we're going to square that together, and that's going to give us a cost for that index at least. And this is only in regards to the data that we have in our training set. This is not going to work if we give it some x that does not have a core, like a y that's provided to our algorithm. So these indexes here, they're only going to relate to the sets that are in these rows here. Does that make sense? So we're going to perform our linear regression function for this x, and we're going to subtract, we're going to take this, whatever we get from that function, and we're going to subtract the this value from it. And then we're going to take that whatever that number is, and we're going to square it. That's what's happening here. Okay, that makes sense. Oops. I don't know why this is tabbing over like this either. I don't like that. Okay, so this cost sum, this is what this is doing is it's starting at 0, but every time we run our loop, we're going to add whatever the new cost is that we have generated. We're going to add to this cost sum. So it's going to create a number that represents the entirety of our data set. So for the length of m, each index in that data set is going to have that value of its cost added to this cost sum as a total. Okay, so and then we're going to take this cost sum, which is a summation, and we're going to divide it by 2. We're going to divide by 2m actually. So it could be divided by 2 or 2m. There's like actually different ways that can work. I don't know like why 2m is the way we're doing it here, but that is apparently the most common thing to do. So I wish I could explain that, but I don't have the answer, unfortunately. So to divide in mathematics, you can just multiply by a fraction with whatever you want to divide in the denominator. So that's what we did here. And this is not in my workshop, but I'm going to print. I'm going to formatted print. We're going to print the total cost. I'm going to get rid of this cell. Did I do this wrong? I think I did this wrong. This is like half of coding is just like Googling things. I actually have some notes for myself here. Oh, should it be a single quote? I didn't think that mattered. Oops. Oh, you know that we know. Okay, my brain is dead right now. This is not gonna work because we're not actually providing any values to it. So what we could do is whenever this gets called, I'll have to do a print statement whenever it gets called. That would make more sense. I could leave this in here so that when it does get called, it'll print that, I guess. That would be nice for the future. So. Okay, so the next thing it says here is cost function intuition. Okay, so I'm just gonna write out a description of like what the point of this is. We have this thing here called intuition, and we're gonna use this to analyze our cost given this function. How do you spell analyzing? Yeah, I spelled it right, didn't I? Okay. Programmers can't type, just in case you don't know that. I don't know if intuition is like some specific technical term. I'm really big on formatting too, so forgive me for taking my sweet little time here. Okay, so I'm gonna write some notes here. It's gonna describe what we're doing in plain English. The goal is to find a model, a linear regression model with parameters. W and B, which will accurately predict house values given an input of X. Yeah, the accuracy is low today. Cost is a measure of how accurate the model is on the training data. So the cost equation, which is this is actually technically called the squared error cost function, because there are different types of cost functions. So the cost function equation above shows that if the weight and bias can be selected, that match can be selected such that the predictions can be selected such that the predictions can just match the target data, and target data is represented by y. The cost term will be 0, and the term will be 0 rather. And the cost will be minimized. Minimize just means that the smallest number possible, because remember the regression line it is whatever you get based on your weight and your bias. You just want to get that smallest cost possible. And there's a formula for doing that called descent gradient, but that's like going to be a future thing. I already know that for this training set, I already know like the answer to the minimized cost. So I'm just going to put that in my notes here for anyone who looks at this. These notes will be on my blog and my LinkedIn, by the way. Okay, so we're going to run plt underscore intuition and train y train. This is going to be a slider. I might be missing something here. No. I think I might be missing something because I'm using this lab utils that I found online. Maybe it's not the right one. Definitely mess up my whole thing here. I'm gonna try something really quick. I'm gonna try this. Nope, that didn't do anything. Oh, I think I might have been inadequately prepared for this. Oh, give me just 1 second. I think I have to download this other. Okay. Yeah, I have a replacement for the utility file that I was using. That might be the more appropriate one. Just give me 1 second to get that set up here. Oh, my Mid-Journey art. I have a lot of it. Okay, give me 1 second. 1 second. Hopefully my little hack here will work. I probably need to restart. Oh, no, I think what's happening. Okay, so there's this file I need. It's like a utility file that's provided by the lab that I'm using here. And, oh, okay. Ooh, I think I might have found it. And within this lab, there's like a certain utility file that I need in order to make this work in my own dev environment. And they don't provide that file because they expect you to just do this within their own thing. But I'm looking through the files for their notebook and I'm trying to see if I can just find that utility file so I can download it and then just use it myself. And I think I might have found it after not realizing, because I had originally gotten like this one. But I guess I just didn't realize that this is like maybe like a proprietary thing. So I'm gonna update the link in the notes for this stream with the correct. I don't know how I should do this. I'll see if there is a GitHub or something for this, and if there is, then I'll update the link for it. But if not, let me just check this file and make sure it's not like copywritten or anything inside of it. Yeah, I don't see any copywriting in this or anything. So what I can do is I can actually host this on my GitHub and then I'll post a link to that for you to use if you would like to. Otherwise, if you're trying to follow along with me, this is not going to work. Or if you're taking that course, it's not going to work in your dev environment without this file. So yeah, my bad. If you've gotten to this point, you're confused like why this part isn't working. So hopefully this works for me as well too. Did I type that incorrectly? Just to make sure. I'm just gonna copy this whole line over. Gonna run all. And I'm going to close this and reopen this. There you go. There. I was literally sweating. Like, am I looking like a fool right now? I mean, I do feel like I look like a fool for a second there, but at least I got it working. Okay, so I'm going to expand this here. So this is basically a interactive visualization. I can't really explain to you like how this is working because this is something that deep learning AI or whoever has created for this course. But what I just showed you a couple moments ago in VS Studio Code, this right here, this is the code that enables this intuition method to work. I'm just gonna look, it's probably gonna be hard for me to read it, but I'm gonna look it up anyways. So it's this here, and there's no type of description of what's going on here. Somehow this right here is allowing this visualization to be rendered. And basically what we have done here is we have assumed a certain, I should probably not close that. We have assumed a certain bias when we're running this. So here the bias is being set to 100. And then the interaction of this interactive diagram, this is actually allowing us to adjust and toggle the weight parameter independent of the bias without us having to rerun the code and do it manually. So you can see here, if you just like look at this point right here, you can see that the weight, which is the slope of the regression line, it's changing. It's changing. And then this here, similarly. So on the left side, this is the regression line, the blue line, and then these red dots, or these red X's rather, these are the actual values from our training data, which is this here. And then on the right side, you can see that there's like this parabola, I think is what this is called. As this gets adjusted, we see that this red dot, this is the cost, that's going to shift, right? And so the goal is to have this red dot be at the lowest point of this parabola as possible, because the lowest point is going to be the lowest cost for our model. And in this case, it's going to be 0. It's the lowest, and it's going to be 0 when the weight is 200. So I'm just going to make a side comment here. The lowest cost is on bias, or B, equals 100, and W equals 200. I don't think italics works with latex, but that's fine. So both of these here confirm our hypothesis is correct. Our hypothesis is the model. The way that this is confirming it is because you can clearly see here that these two data points match up. And the way you can confirm it here is that the cost is at the lowest point on this curve. This on the left side is an unreliable way to work through cost, the value of cost here, because you could actually have data points that are like scattered all throughout this plot. And if that were the case, it would be really hard to visually determine like the best regression line, because the points don't fall like in a convenient, direction or shape. So the reason you do this analysis is for data that is less regular than this, which is what we're going to explore next. Okay, so, whew, I was stressed for a second when that thing wasn't working. I was like, oh no, I'm gonna have to get rid of my stream. I'm gonna have to delete my stream and start over. Okay, so I'm gonna write some notes here before we move on. So, things worth noting above diagrams. Cost for this is minimized when W equals 200. And just remember that the difference between the target and the prediction is squared in the cost equation here. So as the weight, as the weight and everything gets toggled, this cost is going to increase quite rapidly, which is why there is this parabola shape. It's not like linear. This parabola shape is just showing that the way that the weight influences the cost of our function is, it's not like a linear thing, basically. And then the last point here is using So when we have the correct weight and bias, we, like I said, will know that because it's on the lowest point of this parabola. I hope I'm using the right word with that. But also, it would match our data perfectly, at least when we have the ability for that to occur within our data set. Okay, so now moving on for real this time. Cost function, because we're taking in two variables, it is also able to be analyzed in 3 dimensions graphically, which is easier. It can be analyzed in 2 ways actually. I'm going to pull back my notes here. I talked about this in the other video, like part 1 of this, but these are the ways that you can analyze cost function. If you're just dealing with the weight and you have like a static bias or bias size of 0, it is essentially of no consequence. So you can analyze just the weight itself, which is what's happening here. But if you want to analyze visually both the weight and the bias in relationship to the function, then having a 3D graphic is actually better. And the alternate to this 3D surface plot would be to have a contour plot. It's actually hard to see here, but we're gonna make one. So just hold your horses. Just hold your horses. Okay, so we're gonna actually make a new data set here really quick. We're gonna make a larger data set so that we can see this in a more complex form. Is this a header 2? It's a header 3. Okay. Header 3 is a larger data set. Is data set hyphenated? Can someone tell me that? Where's my phone? I need to ask the internet. Okay, so for this larger data set, we're just gonna go ahead and do that here. So X train. Oh, excuse me. We've been at this for a while. How long has my stream been going? How long has my stream been going? Let me see. Let me see. Because I'm just yawning over here. I'm so tired. Oh, I've been at this for a little over an hour. Okay. Not too bad, not too bad, not too bad. We should be able to finish up here pretty quickly. I was thinking that I've been at this for like 2.5 hours. I have really bad ADD, and if you know anything about ADD, you know we do not have internal clock systems. We cannot tell how much time has passed. That is like a part of our brain that does not work correctly. It's classic ADD. So I'm over here feeling like I've been at this for like 50, 11 years, all my life. I feel like a person in a cave comes out after 30 years with a long scraggly beard. Okay, so for this, 250, I'm just copying these numbers from my example, basically. It seems a little crazy, but I do not copy and paste as much as possible. It seems like a silly thing, but trust me, when you don't do it, you're gonna make more mistakes, but those mistakes are gonna help you learn. And you wanna make as many mistakes as possible. As many mistakes as possible. Trust me. You wanna make as many mistakes as possible, as often as possible, if your point is to learn. Okay, so in the contour plot, we'll be able to click on a point to select a weight and a bias. It says here, we will click on a point to select a weight and bias to achieve those contours. Use the contour to guide your selection. Okay, so I'm gonna just write some code here that will render our interactive like charts and diagrams and stuff for cost. Give me just 1 second. I'm not sure what this does, but it says we need it. I think this will probably end this in this stuff here, whatever's happening here. I think it's just gonna close that. I guess I could check, why not? That does not help. Closes the figure window. I don't know. I don't know what plt.close does. That doesn't seem to help me. Okay. So basically, I think it's just going to close like any running things, I guess. I don't know. I'm gonna have to come back and check that. I don't want you to walk away thinking that that's my final answer. Could be wrong. Anyways, I'm just gonna move on because this is not really the point. So what this is just all going to basically do is it's going to create some interactive stuff where we can sort of visualize the cost of this larger data set more effectively, and it's also going to be interactable. This updater is going to have it's going to have the ability to like receive the clicks and stuff on our diagrams. There's a word for that. I can't remember what it is. The word for what it's called when you can receive like clicks and inputs on something. A listener. It's a listener. That's the word for it. Okay. There you go. Ooh, I gotta stretch. I gotta stretch. Okay. So it says here, I'm gonna take these notes because I guess it would be helpful for anyone who will look at this later on. I'm just gonna put them in here. So use the instructed to view a scenario with a few more data points. Actually, I don't like that sentence. I'm gonna leave it out. This data set includes data points that do not fall on the same line. Remember I was saying that in this example here, these two happen to fall on the same line because there's only two, so two things can always be connected by a line. But there are situations where we could have like multiple data points that don't fall as regularly along the same direction. Like here, for example, there'd be no way to have a regression line that connects all of these. So the cost is never going to be absolutely zero because of that. So because the data points don't fall on the same line, the cost can never be zero. In the course, it's like asking, can the cost be, given a specific W and B, can the cost be zero? The answer is no, but it's posing it as a question just for the purpose of the course, and I know the answer is no. So in the contour plot, which is this one, this is the one that I was like saying here, it's really small. This is a contour plot, and what it is a cross-section of our soup bowl. This is called a soup bowl. Soup bowl is like this. And is this in our contour plot? This contour plot is like a cross section. So the colors here, it's like color coded. And the lowest cost, which on this diagram here is like the bottom of this parabola. The same thing is true for the soup bowl. If you can imagine that there's like a point at the very bottom of this soup bowl, whatever that most bottom point is, that would be the lowest cost. And then on our contour, the lowest cost is going to be just right in the center of this contour, right at the most center. If you think about this as like a topological contour, a contour is like they represent the height of spaces. Like a map, if you look at a contour of a mountain, for example, this is kind of like the reverse. The closer you get to the middle, the lower this is, like in 3 dimensions, and the lower it is, the closer it is to zero. And that is along this x-axis, which is the function of the cost function. Okay, so it says here in the contour plot, which is this one, click on a point to select a weight and a bias. Weight is the x-axis and bias is the y-axis. So I'm gonna do 200 and 100, just like what we did in the previous one. So you can see here it's changing it. And the cost is 5,277. By the way, you see how there's like a line drawn between each of these scatter points and the regression line, and there's like a number here. Each of these numbers is the value that is that we get or that we derive from each of these squaring operations here. I hope that makes sense, but each time you do this for every index within our data set, you get a number, and that number is this right here. It's the cost. And we take this entire, all these numbers here, and we add them together. That's called summation. That's what our loop is doing. And then we take all these numbers and we divide them by, here it's doing it by m, but in our function here, we're doing 2m. I think 2m or m is both of those are viable options. So I don't know if there is a lowest cost, but I know that if I put my point at the most center here, I can kind of get close to, I can get the lowest possible for at least this data set, and I got 1,738. There is a formula that will automatically determine what the lowest cost is. It's called a gradient descent. I think I have mentioned that, and that would be like, and I don't know if it'll be the next topic because I'm going to do a review video for this first, but it'll be the topic after that. You can also see here as I move these points that it's moving in our soup bowl here. So like this most outer fringe, the regression line is really far away from our data, and it's also really high up in our soup bowl. And then when it's like in the middle, which is approaching our lowest cost, then it's like going to be toward the center of the soup bowl. Okay, so it says note above the dashed lines in the left plot here. These lines here, they represent the portion of the cost contributed to each example in the data and training set. I'm just going to write that out too. I already explained that, but I'm going to put in my notes for anyone who looks at these. Represents the training set. Each example in the training set. Actually, I'm not going to do M. M is the length. How should I say that? Each example in the training set. I don't know if there's like a specific. I can do it like this. This is going to take a lot of latex. Let me see if I can just take this here. There you go. Oh, I forgot my dollar signs. Okay, so for each in our training set, comma, So it says here that the values for weight, if the value of the weight was 209 and the bias was 2.4, that would provide us the lowest cost for this particular set of data. I guess I'll put that in here. And so now we're gonna do like another like independent soup bowl. They're calling it here convex cost surface, but it's just gonna be a soup bowl. I'm gonna check their code really quick because it seems like, oh, I can rotate this. Well, look at God. That's cool. That's pretty cool. That makes it a lot easier to see. I'm trying to figure out like updater equals. Never mind. Ignore me. Okay, so we're gonna render our soup bowl. I spelled soup wrong. What's up, bowl? This is sup bowl. It's beautiful. It's beautiful. Look at that. Look at that. Okay, so the fact that the cost function squares the loss ensures that the error surface is convex like a soup bowl. And that's like similar to this parabola. Think about this parabola just being in 3 dimensions, but it includes a z-axis, which is for the bias. That's what this is here. I should probably put that in some notes here. So the error by the way, just how I'm studying right now, I'll tell you, like, this process of like thinking through your problems and talking through them out loud and kind of just giving yourself the space to just like awkwardly struggle, but do it out loud in a very explicit way. Like, that is very helpful as a software engineer. You will learn so much faster when you just do it, like study in a very like awkward way. Expose all of your misunderstandings, like talk out loud, get you a yellow duck. That's traditionally how they do it. You'll learn so much faster and so much more thoroughly. And if you can, stream, record yourself, whatever you got to do, and listen to yourself. I'll come back to that at the end of the stream, and then that'll be the end. So I'll come back to that topic because I think that's important to talk about. So I'll say here, similar to the parabola parabola rendered by the code on line 6. I'm gonna make that this, except it includes a z axis which represents the always have the minimum that can be reached by following the gradient in all dimensions. So what that means here is like this gradient, the gradient is this shift in color, right? This gradient is descending down towards a minimum. If you look at this direction here, you'll see that there's this point at the very bottom, So this gradient descent, if you follow this, it'll always lead you from any position on the outer corners or the exterior. If you follow that gradient and descend towards the base of this soup bowl, it'll always lead you toward that minimum cost, where the blue and the purple is. It's always going to be in the middle of that. I don't know if this soup bowl always is going to look symmetrical like this. That's something I have yet to explore. But the gradient descent is always going to lead you toward the base. And gradient descent is also the name of that algorithm that I keep mentioning. So the minimum can always be reached by following the descent of the gradient. I guess I just answered my own question in my mind, because I was asking just a second ago whether or not this can be asymmetrical or whether or not this can take on different types of shapes. And I think the answer is yes, because if you look here, I'll just explain this real quick. The weight here is on the y-axis, and the cost function is on the the weight is on the x-axis, and the cost function is on the y-axis, and the bias is on the z-axis, and the bias and the weight can be toggled independently. So that means that these corners could be, in theory, be stretched out in different ways, and this shape could be contorted in a way, flattened out, or even more dramatic. So that would just be because these weights and biases and whatever are being toggled independently. So basically, that's kind of like my study session. I'm going to come back and do a review for this. This is kind of an awkward ending, but I'm also pretty tired because we've been doing this for a while. But this is something that I think is really helpful. Before I let you go, I want to revisit the thing I just said I was going to come back to. Studying code is difficult and challenging. But one thing I find easy, and the reason why I make these videos for this tutorial series, is because like even though I'm learning, I don't want to wait until I have mastered something to explain it. And that kind of is like counterintuitive, but when you have to explain something, it forces you to recognize what you don't know and what you don't understand. And as someone who's trying to learn something, especially learn something new, like you're going to benefit a lot from just forcing yourself to go through that awkwardness. Now, that doesn't mean you have to stream or, do commentary review videos or, tutorials and stuff like that, unless you're a crazy person like me. But it does help, I think, to, even if just privately, to record yourself explaining things, because the reason why I make this series in all reality isn't necessarily to get viewers and like followers. It's because I actually go back and I watch these videos and I analyze, like, am I making sense? Was I able to explain something well? Could I explain this concept to someone who didn't understand it? And like for me, those are all metrics. That's like my rubric for validating whether or not I've like ingested the juice, the meat, the substance of whatever it is I'm trying to learn. So I encourage you to do that, even if you're not in the process of actively learning, but you just have to explain something. One thing that a lot of programmers do is like they'll get a rubber duck and they'll talk to the rubber duck as if it's a person. And like it's like a cliche at this point. It's like a kind of just like a thing a lot of people just do. But it's like for the same reason. Whenever you have to explain something, when you're learning it, that is like a part of the learning process. And they often say that the thing that makes a person a master at something is when you have like when you figured out how could you explain what you think you understand, because if you can't explain it, you probably don't understand it, you know. And yeah, I just encourage you to not be afraid to share what you're learning, not be afraid to explain what you're learning, and not be afraid to receive feedback. Even the most experienced programmers, people working professionally and stuff like that, seniors and whatever, like even those people sometimes struggle to explain and to communicate what's going on with like their code and stuff and like their math. And it's because like when things are internalized in our minds, it's really hard to know whether or not we actually make sense until we have to speak them out loud, or until we have to write something out loud or on paper. So I don't know why I feel like I have to explain that, but I hope that that kind of like puts this series in context and also encourages you to maybe think about doing your own. I'm really just going to go through the rest of this course, as well as other things like other projects and stuff that I do, and I'm going to try my best to make them available. But for this particular video, and for ones where I feel like maybe I struggle to explain things, I will come back and do a video that is specifically titled review. And I'll make sure that videos like this that are just like study sessions are appropriately labeled so you don't get confused. But anyways, that's all for now. Thanks for coming by, and I'll catch you later on. Peace. Peace, peace, peace.